own work of very wide scope work on networks. So he'll be talking today and then tomorrow at 2.
Yes.
Okay? And then I, myself, will be talking today at 2 and tomorrow at 3. Okay? That's the plan. Okay? Very good. So without anything further, please, Sanjeev.
Okay. Thank you, Fernando, and very happy to be here. So I wasn't entirely sure what was expected. Initially, I was given the impression that there might be 2-hour lectures, and then I'm now realized it's a 1-hour lecture. So I have decided to present a paper, but what I'll do is to, I don't think I'll have time actually to go through all the technical details, and I imagine there is a very diverse background, different people here come from very different backgrounds. So what I'll try and do is to give you some overall, overview of some of the questions that I think are important here in this field. And I understand that Fernando will be talking also about trading in networks.
From perspective of
later today or tomorrow?
Today.
Today, yeah, so that's great. So you will see that they are kind of broadly very related. And so at a high level, the perspective that informs this work is the idea that markets are really networks. Okay, and so in other words, you have traders in these markets, and they buy and sell, and sometimes they resell. And the key sort of feature of this work is that there are interesting and complicated relationships between these traders, so that some people can trade with some others, but not with everyone. Okay, so in other words, there are restrictions on who can trade with whom. Okay, and those restrictions are modeled as networks. Okay, so I can trade with you if I have a link with you, and I can trade with you and you can trade with someone else, and therefore I can trade indirectly with someone via you. Now, in a classical sort of Walrasian model, everyone can trade with everyone, so that one would think of as a complete network, okay, where everyone can trade with everyone. But generally, for a variety of reasons, networks are not complete in the world out there, and therefore it's interesting to ask how the network structures, which reflect different patterns of frictions, if you like, in the market, how they affect the trade, how they affect the functioning of this market. Okay, so this is really what's going on here is we are looking at the intersection of frictions in exchange or production on the one hand, and some exchange itself. So it could be price formation, it could be auctions, it could be bargaining, and I think Fernando is going to talk about bargaining in his work. I'm going to talk mostly about price formation process where people post prices. So I post a price and you can take it or leave it. Okay, so there's no bargaining. Okay, and I think maybe Fernando might talk a bit about auctions, and I'll maybe make some remarks on auctions, but that's another way in which prices are formed in markets. Okay, so just to summarize, what we are doing here is we are thinking of markets as a network, and I'm going to be talking mostly about intermediation. Okay, so I'll be mostly interested in a setting where there are chains between the source and the destination. Okay, and let me give you an example of that. Here's a simple network. So you have home, you have the loop, this is the source destination, and you have a bunch of people sitting on the paths between the source and destination. And these guys are setting prices. They are sort of profit maximizing agents. And when you want to go from home to the loop, you compare the paths, the different paths, and you look at the prices, the cost of using different paths. Okay, so another example would be the coffee chain, where you have a farmer, you have a consumer at the end, and the farmer sells to the local intermediary, who sells to an exporter, who sells to a broker, who sells to Nestle, a roaster, who sells to a grocery shop, and then the consumer buys these things. Again, what's going on here is it's a slightly different setting where the farmer doesn't really care about what happens to the coffee when it reaches the consumer. His main desire is to sell his coffee at the highest price to make the most money. Likewise, the intermediary here wants to sell at the highest price to the exporter. So you don't compare the cost of the entire path, but you just look locally at each point, who to sell it to. Okay. But the idea is, again, at a high level, it's really very, there are many other applications with this. So you can think of these as banks. You have a depositor and you have a project, and you have different banks sitting in there, and they are trying to get their margins by intermediating between they buy or borrow and then they lend. Okay. So there are many different applications. There are many different applications where you have this feature that you're traversing a network, and not everybody is connected to everyone in this network. Okay. And so we want to understand how the network structure of the chain shapes market power and determines prices and efficiency. That's the once you understand this, you can then ask questions about whether you should have entry, whether there will be entry, whether you should allow mergers between different players, whether these chains are going to be there will be enough entry, they will be resilient. If there are some shocks on the system, whether the system will collapse or whether there's enough redundancy in the system so that if some people break down, you will still have active paths elsewhere. Okay, so those kinds of questions will all, if you like, to understand those, you have to understand for any network what happens, what are the profit-making opportunities, and what are the welfare implications. Okay, so this is, if you like, a first step in understanding what kinds of networks will form and whether they will have desirable properties. Okay, so what I'll be doing is I'm going to present to you a very, very simple first model, and I'll go through it reasonably quickly, and you will see that it's quite tractable in some ways, and then, time permitting, I'll talk about a number of other extensions, a number of, if you like, complications you can introduce into this model, which really expand the scope of the analysis. Okay, so the model here is, as I showed you in the picture, there's a source S and a destination D. The path between the two is a sequence of interconnected nodes. The passage from the source to destination generates a value. Intermediaries simultaneously post a price to get a share of this value. Prices determine a cost for every path between the source and destination. The good, or the journey, or the coffee moves along the least cost path, and an intermediary earns payoffs only if she is located on that path. So we study Nash equilibrium of this setting. Okay, is this game clear? Okay. So we look at Nash equilibrium of this game, and here's the main result in this model. So in this very simple setting, it's going to turn out that you're going to make money, or you're going to set high prices if and only if you are critical. Okay, so the theory we will see is quite permissive. All sorts of equilibria could be around, but when we combine that with experiments, then we see that the main takeaway is that criticality of a node defines market power and shapes pricing, earnings, and the efficiency of economic activity. Okay, so what's a critical node? A node is critical if it lies on all paths. So let's just go back and look at this picture. So in this coffee network, coffee trading network, or supply chain network, you see that E1 lies on all paths, but it's the only player who lies on all paths. So E1 is critical. You can see that, for instance, R1 is not critical. If R1 drops out, you can still trade through R2. So it's a very simple idea. Likewise here, you see that the Eurostar, the channel crossing, is a critical player in this particular network. Okay, all the other guys are non-critical. So what we're going to see, the main takeaway message of the first part of the talk is going to be that if everyone's setting prices, there could be lots of things happening in the theory. In fact, there are a lot of different equilibria. But if you take this game, if you take it to the laboratory, then you're going to get this result. Okay. All right. So let me just give you a quick, very quick overview of the literature. As I said, we are combining networks and an industrial organization of markets, and I talked about experiments. So these slides are available, right, on here. So some of you may be interested in, the background literature, and so this gives you, I don't think it's complete because, I haven't given journal names, etc., but you should be able to get a lot of idea, what the literature is by just scanning through some of these slides. I wanted to say a few words about how to see some of this work. So what we're really doing is we're playing a game on a given network. So in a sense, this is a particular case of a game on a network. And I don't know whether you had lectures on games on networks, but this is a specific instance of a game on a fixed network. So that's the sense in which it's part of network theory and the work on games on networks. It's very much related to market power in complicated environments, so it's very central to industrial organization, the theory of industrial organization. And finally, there has been a lot of interest recently in empirical work on intermediated markets. And in particular, the Lee and Schurhoff paper is a very nice paper on what are the margins that banks charge and how these margins are related to the location of these banks in the network. Okay, this is a paper on municipal bonds. These municipalities in the US issue bonds, and they sell them to banks, which then sell them downstream further to other banks. And the question is, how much money do these banks make? And Lee and Schurhoff mapped this network and show that the margins are very highly related to location of these banks in the network. So there's been a lot of interest in understanding the empirical structure of these intermediated markets, and I've just given two references, but there's a lot of other work now looking at that. So,
clarification.
Yes.
Question. Your networks in this model are binary edges in the sense that either you can trade with another node for some cost that's common to all these edges, or you can't trade at all.
That's right.
So there's no sense of it's twice as costly just to use this link versus that link.
Yeah, so it's a limiting case. You can either trade or you can't.
I see.
Yeah, so it's either infinitely, there are no capacity constraints here either. So I'll come back to how one can extend some of this, to do that. But yeah, it's a good point. One might, for instance, if you think of the transport network, you could have every link has a cost, if you like, or alternatively, every node has a certain cost for bearing the traffic, and there is actually ongoing work with that sort of thing. So just to clarify what I mean by that, so in the model I'll talk about so every possible trade is possible on the paths that are outlined here, and there's no cost, and you can only trade on these paths. But you could say a natural way to take this forward would be to say that this every node here has a cost of production, if you like, okay, and it may even be non-linear. Okay, so if you want to go through here, then you have to bear a cost, and that's and so it could be you have a short path, but it's very costly. The path might be costly, but it's a short path, or you could have long paths which are less costly. So those sorts of variations can be introduced, and indeed people are now working on those. But at the moment, the costs for these nodes are zero. Okay, so it's a pure price game. So let me make it a little more formal. So as I said, here's the, so define Q star, okay, as, so Q is the set of parts, and so Q star is a set of parts which have minimum cost, okay, given the price profile P and the network G. And given G and P, G is a network, P is the price profile of all the players, the payoffs to the intermediary, I, are given by this equation 1. So if you lie on the cheapest cost path, then, if you don't, then you don't get anything. And if you do lie on the cheapest cost path, then you get money depending on how many of these paths you lie on, because they are picked randomly. So eta is the number of paths, cheapest cost paths that you lie on, and Q star is the total number of paths. So one of them is picked at random. Okay, is the game clear? Everyone posts the price. So you have a price P1 to Pn. Given that price profile and given the network, for every path I have a cost. I will call that C of QP. I'm only interested in the cheapest cost paths. That's a set calligraphic Q star. And if I now look at a trader, this trader makes money only if she lies on the cheapest cost path. And when she does make money, she makes PI. That's her price. And the probability she's on the, she's going to be picked is just the number of cheapest cost paths she lies on. Okay. So here's a different, in finance and in coffee chains and so on, one can imagine that you don't put a single price, but you actually post two prices. You post a buy price and you post a sell price. Okay, this is very common in financial markets. You have a bid ask. Okay. So this slide talks a little bit about the relationship between my simpler model and this bid ask model. Okay, so I won't really, explain everything in this thing. Let me just sort of give you a flavor of what's really going on here. Let me try and do it. Okay, so the first observation is that in any network that you give me, there's going to be a pure strategy equilibrium that is efficient. In other words, there will be trade in the equilibrium. How do you construct that equilibrium? Well, let me just go back to the simple picture, just to give you a flavor of how you construct equilibrium. So you take this picture, and what you do is you identify critical players and non-critical players. Okay, so in this network, there is one critical player, and everyone else is non-critical. So now you say that all the non-critical players set a price 0. Okay, so all these guys, these two players set a price 0, and this guy sets a price 1. Let's say that's the size of the surplus. And my claim is that's an equilibrium. It is an equilibrium because the non-critical guys, if they were to raise their price, there will be no trade, so they can't make any money. And the critical trader can't increase his profits because the total surplus is 1 and he's extracting the entire surplus. If there were if there was multiple critical traders, you could then allocate the money they have between the different traders, between the different critical traders, and have that sum up to 1. Okay? That's the construction of equilibrium. Okay. So that's how you construct an efficient equilibrium, but the problem is somewhat complicated because there can be lots of inefficient equilibrium. Okay, and what the rest of this theorem does is actually gives you a complete characterization. It tells you everything that can possibly happen in this model. Okay. So let me just highlight 1 or 2 points about this result. The first point is that the simplicity of the model means that you will either have all surplus going to the traders or all surplus going to the buyer and seller, okay, the source and destination. So in other words, if you look at this first line, if you're having trade, then traders extract all the surplus, in which case C of P star is equal to 1. The surplus here is given by 1, or they earn nothing. So C of P star is equal to 0. Okay, so that's because of the simplicity of the model, you get extreme outcomes. And so you can't have sharing of the cake between the source and destination and the intermediaries. And this part of the theorem is basically giving you a finer idea about all the different things that can happen. But instead of going through the details of this, let me give you an idea about what happens in this model. Okay, just to give you. So let's look at a very simple network. Okay, so let's look at this. So let's just look at this network where the source is here and the destination is here. Okay, and this network, you can see, illustrates many of the issues in a very simple way. So now, notice there are no critical traders, because supposing you take this guy, you can always go through this path, so there's no critical trader. So we know there's one equilibrium in which all the prices are 0. So that's certainly one candidate for equilibrium, and you can check it's an equilibrium. But there are many other things that could be happening. One of them is that all of these guys miscoordinate. So they set very high price, and you can check that this outcome where all the traders set a price 1, which is a complete breakdown of coordination, is an equilibrium, because once these guys, let's say all these traders have set a price 1, there's nothing this person can do to make money. He might as well set a price 1, that guarantees there's no trade, but he can't possibly make any money as long as if he sets any positive price, epsilon, it would be too much given the surplus, it would be 1 plus epsilon, there would be no trade. So this is an equilibrium. And then finally there's a third equilibrium in which this path, for instance, sets a price 1, and this path coordinates successfully. So this guy sets a price P1, and this guy sets a price 1 minus P1. Okay. That's another equilibrium. So there are 3 pure strategy equilibria here, and you can see that they have very different properties. And moreover, you can also see that 2 of them are efficient. So the 0 equilibrium is efficient, and this P1, 1 minus P1 equilibrium is efficient, this trade. But you also see that in the equilibrium you have extremal outcomes. When you have the 0 price equilibrium, all the surplus stays with the source and destination. When you have the P1, 1 minus P1 equilibrium, all the surplus goes to the 2 intermediaries. Okay. So even in the simple setting, you can have a very wide range of outcomes. Okay. So the theory is quite permissive.
So here the P1 is just a parameter that parameterizes all possible equilibrium of the sort.
Yes.
P1 is undetermined.
Yeah, so P1 is undetermined. Yes, that's right. So this motivated us to take this model to the lab. Okay. So notice that I've shown you an equilibrium where there is no critical trader, but there is an equilibrium where the intermediaries extract the entire surplus. Okay. So, so criticality is sufficient, but it's not necessary.
Can I interrupt you?
Yes.
Because in this question, if you introduce some sort of discount with or some sort of sequential bargaining or sequential posting, if you wish, with discount, then this P1 would be uniquely determined, or not? In more
So what you're saying is that supposing you have a setting where what you do is at each step you look at the guy, you start from the source, you're sequencing it in the sense you first look at the first layer.
That's right.
And they set a price, and then the second layer they set a price.
Yes.
And you're saying that in that setting you would expect that, so for example in the simple network, these guys should extract the full surplus. They are upmarket.
Mm-hmm.
That's what you're saying.
Yes, I'm not really
Yeah.
sure exactly what.
Yeah, and then,
this sort of yes.
So let me just make, so it's a very good point. Let me make a few remarks. So So there is work on sequential trading. Okay, so we haven't done this in this paper, but there is some ongoing work by Matt Leister, who's a student at Berkeley, which actually does sequential trading in these kinds of networks. But one has to be careful, because I think if you want to run sequential models, you have to have a lot of structure in the graph, so that you have a well-defined layer like this, and you sequence the pricing layer by layer somehow in terms of the timing. So another way to put it is that you can imagine that the way to sequence, there are different ways of sequencing it, but it's so the way Matt Leister and his co-authors work on it is that they actually have what are known as multipartite graphs. They don't allow for general graphs. Okay, and I can talk a bit about why they need that structure, but as things stand, we are allowing for arbitrary graphs, and so one would need slightly different sequencing to get it to work. But it's a good point, and in a paper that I have with Piero Gottardi, we in fact do exactly that. We look at sequential. When I own the good, I can post prices. Okay, I can post demands, and then you can, we do some of that, and I think there's varieties of but here, so let me just say that in a setting where you have full information, okay, about the network and full information about the valuation, when you own the good, you can actually extract the whole surplus. It's quite straightforward because you can make an entire good. So it's somewhat uninteresting, if you like.
I have a question.
Yes.
Maybe I still don't understand the model. I don't see why 1,111 is in equilibrium, because if one agent changes the price to 1 minus epsilon, then all of the good passes along that path, and then they get more.
No, so notice that one of the assumptions in this model is that there's a surplus which is fixed, and the surplus is 1. Oops. Okay, the surplus is 1. So that means that if my partner, the path has set 1, the only way I can get trade to occur is that I set a price 0.
I see.
Okay, so we did do a number of refinements. We didn't do, so I think, the conjecture I would have here is that if you do sequential trading with the formulation that you can demand the price when you own the good, I think it should be trivial in this setting. I suspect you should basically get you'll extract full surplus. So the source will extract full surplus. Basically demand the price of 1, and everyone down the line will just demand a price of 1. Will pay 1 and then demand a price of 1, all the way down to the buyer, the destination. That's what's going to happen in the simple sense. Okay, so so what we did was we ran experiments. Okay, so remember the issue was there are many equilibria. In some equilibria, you have these non-critical guys making money, and and I'll discuss another issue that you can also have when you have critical and non-critical traders. You can actually have non-critical traders make money. Okay, and I'll explain that with this picture in a moment. So here is the design of the experiment. We have 4 treatments. The rings 4, 6, and 10 have the feature that there are 2 paths between the source and destination. So there are no critical traders, and the ring with hubs and spokes has the feature that if you can have, so let's look at this case. This is the network, and let's say that the source is A1 and the destination is E1. Okay. So now you can see that you can come down this route. That's one possible path. And you can also go across on the longer route. Okay, so now you see that A and E are critical traders, and F, B, C, and D are non-critical, okay, because there are two alternative paths. So really the question is what would happen here, and will the critical traders take most of the money, set a high price, or will they share the surplus with the non-critical traders? And it's easy to see with, if you think for 5 minutes, that you can actually construct equilibria in this simple setting where most of the surplus actually goes to the non-critical traders. Okay. How would you do that? Well, here's an example of an equilibrium. Imagine that these three non-critical traders all set a price 1. This non-critical trader sets a price 1, and then the two critical traders set a price 0. So that's an equilibrium. Why is it an equilibrium? Well, the critical traders can't raise their price. If they did, trade would break down because this guy is extracting full surplus. How can he make money? He can make money because these three guys have set a very high price. They have priced themselves out of the market. So you see a very bizarre kind of an outcome where the non-critical guy F makes all the money. That's an equilibrium. Okay, so we wanted to ask whether things like this happen in the laboratory. So this is a fairly complicated environment. If you have a ring with 10 guys, you could be coordinating. So if you look at the ring with 10 people, you could have a situation where the distance between the source and destination is 5, which is, they are on opposite ends of the ring. And in spite of that, we see 100% trade. So this is quite remarkable that you get trade, you get efficient outcomes all the time. And even in the ring with hubs and spokes, essentially you get trade pretty much all the time. Okay, so this is quite surprising, and it's in line with earlier tradition in economics experiments that there's a lot of pressure towards efficient outcomes.
How do you experiment that? What is the design? They post prices simultaneously?
Yes, so here's the design.
How can they
We ran, so fix the treatment, so fix the ring. So we run this ring 60 times, okay? And the idea is that, so let's fix our minds, and let's say that we're looking at this treatment, ring 6, okay? So what's going to happen is, we are going to have this treatment, so we're going to have 2 sessions. In a session, we have 18 subjects come in, so there will be 3 rings formed at any round, and so we allocate these people randomly into 3 rings, and then at the end of the round, we reallocate them into rings, so as to reduce the repeated game element. Okay? And so these 18 guys play 60 rounds, and they get paid depending on how much money they make, the prices, and so on. Okay? They get paid in every round, and they're reallocated. So now at the end of the round, they are reallocated across the rings, and then we pick the source and destination, and they are passive, and the non-source and destination, they are the intermediaries, and they set prices simultaneously. Okay, and once the prices are chosen, then the cheapest parts are picked, and amongst the cheapest parts, one of them is picked at random. That's the
Source and destination, you get money?
They get the residual. So
They get the
so
residual.
yeah, so they get the residual.
Excuse me, I have a question actually about learning bit, because although you reallocate them, was there any correlation between the previous profits of the particular place and the price they would be setting next round?
Sure. That's the reason why we have 60 rounds, because it's a complicated problem. You want people to learn how the game is played. And I don't think I have data here, but we ran 60 rounds, and in fact, we have data on all the rounds. So we can actually, let me see, I don't think actually I'm going to talk about, so I won't have time to talk about. So yeah, the learning issue, are prices moving around, are they settling down over time, and is there, are particular traders doing different things, and all of that, actually we have data, but I'm going to present just aggregate patterns today, okay, but you're right. So the second finding is about the role of critical traders, and this picture is quite clear. What's happening here is on the left-hand side, you have the rings, 4, 6, and 10, there are no critical traders. On the right hand side, you have the ring with hubs and spokes. There is a critical trader, and what you see here is that the number of paths is 1. If you have just one path, then of course everyone is critical of the path. So here the distance is 2, which means there's 1 critical trader, and here the distance is 3, which means there are 2 critical traders. And what you see is, if you look up on the y-axis, I'm looking at the intermediation surplus extraction, and you see that you basically get almost like 100% surplus extraction. Okay. So what exactly is this treatment? These two treatments, they correspond to the case where you have a source here and destination here. So there's 1 critical trader and the distance is 2. Alternatively, you could have the case where the source is here and the destination is here. So the distance is 1, 2, 3, and there are 2 critical traders. Okay. And in these two cases, you have full surplus extraction. If you have no critical traders, there's essentially very modest surplus extraction, under 20%. So 80% of the surplus remains with the source and destination. The other treatments here reflect, more complicated patterns. And essentially, what you're seeing here is you're having a mix of critical and non-critical traders. Okay? And when you have a mix like that, you actually get less surplus extraction. Okay? So that's the takeaway, that when you have a mix of the two, there's a lot of strategic interaction, and essentially more surplus is left on the table for the source and destination. So let's dig a little deeper into the critical. So let me give you an idea by looking at a particular. So what's going on here is, this is the source and this is the destination. So we have 1 critical trader here, and there are 2 paths. There's a long path and a short path. So what goes on here is very clear. The long path is competing quite vigorously with the short path. So if you add up these prices, they are slightly higher than the prices on the short path, but not massively higher. And indeed, you will see that 1/3 of the time, trade actually happens on the on the longer path. Okay. The other point to take away is that the critical trader takes a very large cut. It takes about half the total surplus. And but you see that not all the surplus is extracted, but the intermediaries, roughly 20-25%, is left on the table for the source and destination. When you have 2 critical traders, you have the 2 critical traders more or less setting symmetric prices. This is from the lab data. And again, you see that the short and the long paths are competing vigorously. So you see this pattern here, and what do we see here? We see that you see, if you look at the rounds 41 to 60, you see that this is the number of critical traders. Here he's making 67% of the surplus he's taking, and likewise here, if you have 2 critical traders, they take about 80% of the surplus. So, and this slide sort of explains to you the origins of where these profits are coming from, and you see, again, on the right hand side, you have the treatments with critical traders. The black circle is the critical traders' prices, and the red cross is the pricing by the short path trader. The blue is the pricing by the long path trader. And what you see here is that, again, the critical trader sets a much higher price compared to the non-critical traders, and the non-critical trader on the shorter path sets a price much larger than the non-critical trader on the longer path. Okay, and that's also true in the rings. These are the, so let's look at ring 6. You can be on the short side or the long side. The short side guy sets the price around 15, and the long side guy sets the price around 5. There are 3 of them, so the prices are roughly comparable.
So these are average shares of the surplus over the different say, final rounds or something like this?
Yeah, this is the last 20 rounds.
The last 20 rounds.
Yeah, this is the pricing, average pricing.
And then Yes, level pricing. So then still you do have in these last rounds efficiency. So there is
That's right.
no surplus wasted,
Yes,
which is remarkable
it
because
is. Yes.
because there is this still this multiple equilibria that could give rise to a significant probability of miscoordination.
Yes. Yes.
Which somehow is
It never
constant.
happens. Yeah. It is quite
Which is,
extraordinary.
but then probably what happens is that a certain group just settles in one of these equilibrium, and then just sort of keeps playing that all the time. So then in that sense, in each group there is no such equilibrium uncertainty in a sense, because in each group somehow for some reason the
The
group
groups are moving, right?
the groups are moving.
Yeah,
that's right. So
the
then there
groups
is
are
no
moving
So
across.
that's very remarkable that
Yeah.
this happens. I cannot understand. We can talk about this later, but I don't understand.
Yeah, no, this is very, I think it's quite striking that, notice that, it is quite striking because if you go back here, you see here, when you have ring 10, and you have the shortest path is 5, really what's going on is that you have the source here, the destination here. So there are 4 guys on either path, and they have to compete, and they have to coordinate. And in spite of that, you get, 100% trade. But of course, the prices are, it's interesting. They are all, the extraction surplus is very modest. It's just 20%. So in other words, average total prices are around 20.
Actually, I have a question. Did you actually saw any adjustment? Because one thing which I kind of may imagine happening is that people just saw what other people were putting beforehand and just copycat it, just without thinking.
Yeah, so the paper is actually very long already. So we did not do a very, there's a fair bit of discussion about the dynamics, but we did not do a systematic study of the learning dynamics because they are not kind of very dramatic, and we focused mostly on the last 20 rounds. But yes, the data is there, and you could look at these kinds of questions. Okay, so
One question?
yes,
Can you please redefine efficiency in the model?
efficiency here just means there's trade, because there's surplus of 1, and you get efficient outcome whenever there's trade. If you have a breakdown of trade, because these guys set prices larger than 1, then you have breakdown.
So it's either 100% efficient or 0%.
That's right, exactly. In a particular round. Yeah. Okay. Okay, so this slide is about competition on paths, and what it's really saying is that these paths are competing vigorously because, let's say if you look at rings 10, 1/3 of the time, trade actually happens on the longer path. So that's sort of, they're setting prices very close to on the 2 paths. Okay, so you get efficiency in the lab. There are multiple equilibria, inefficient equilibria. In the theory, they're all washed out. Of course, you don't get equilibrium behavior in the sense that you don't get 0 prices or 100% prices, but when you have no critical traders, you get prices very close to 20% total price. So it's close to the 0 equilibrium. And when you have a critical trader, it's close to 70, 75% to 90% extraction. So it's again extreme. And when you have critical traders, they set much higher prices and they take most of the surplus, 70 to 80% of the surplus extraction. So in other words, the laboratory, goes a long way beyond the theory because it sort of picks particular equilibria, if you like, roughly, and it picks particular traders in those equilibria as making money. So people seem to be very sensitive to network location in their pricing behavior, which is quite, of course, if you come from the experimental end of this literature, this result that you have almost full extraction goes against all this literature on ultimatum games and dictator games where people are fairness oriented, so they actually leave a lot of the surplus for the other trader. Here they take most of the surplus. So it sort of speaks to that literature.
It's a very different game. It's not there's no
Yes.
response of, no?
Yeah, but if you are here, okay, and you're choosing, and this is the source, this is the destination, this is really a dictator game, because essentially when you choose a price, you're saying what you're announcing a split of the cake.
Sure, but there is no sequential move. And the dictator, not,
Yeah.
not in automatic, the
Yes,
dictator.
that's right. Yeah. So yeah, I mean it's okay. So it's
I don't understand one thing. That you say that the.
Yeah, I'm just
sorry,
keeping it
I
up,
should,
yeah.
I should just.
no, go ahead.
No, you say that the division is extremal, which, if I understand correctly, basically meant that either all the intermediaries get the surplus or the source and destination of the surplus. No? That's what your definition of extremal means. What's extremal?
Yes, that's right.
That's extremal.
Yes.
Okay, I see. No, I see. So then you say, okay, basically it is, I see. So the source, so basically that the fraction of the fraction that of the surplus that the intermediaries extract is either very close to zero or
That's
close
right.
to 100
Yeah.
as a group.
Yes.
As a group.
Yes.
That's what it is.
Yeah.
Okay.
Okay, so what I'll do is I won't really go through these extensions in great detail, but I want to sort of talk a bit about different ways in which one can think about this problem, which is more general. Okay. And so let me go back, and I'll just spend about 10 minutes talking about a number of different projects that are going on now, different people are working on. Okay, so I think there are a number of issues that that arise in this sort of a setting, and I'll very briefly go through three of them. Okay, so the first one is information. Okay, so, and there are two kinds of information issues. One information issue has to do with knowing the network. Okay. Now, in some settings, in a small network setting, it's quite reasonable to believe that you know the full structure of the network. When I worked out the equilibrium, I was assuming that you know the full structure of the network. Okay. Another way to think about that would be that you know the network, but you don't know where the demand and supply are coming from. Okay. So supposing you are, imagine that you're a train company and you're setting a price. And I'm going from Cambridge to London, but it could be I just go to London and I stop. Or it could be that I carry on and I go to Bristol. Okay? But you may, the pricing as I defined it was a one-shot price. It was a single price. Okay? So in other words, there's no price discrimination allowed. Okay? But of course, in many network settings, you may know the network, but you may be obliged to set the same price for all source destination pairs. In other words, you may be obliged to set a uniform price. Of course, if you could discriminate perfectly across source destination pairs, you would be in the model I went through. But if you can't, then you are looking at source and destination emerging randomly in this network, and you have to set prices. And the idea there is that you have to trade off. If you set a high price, you will get a lot of money in the local trade, okay, the local guys who are coming very close to you. But people who are traveling long distance, if you set a high price, you will lose all of them, because if all the traders set a high price, those journeys or those trades will become unattractive. That's the trade-off. That's different from the trade-off I've looked at here, and it's a little smoother. Okay, so there's some interest in that problem. Broadly, it's about whether you can do perfect price discrimination or whether you have to set uniform prices, how that interacts with networks and so on. Okay, so that's one set of issues. The other set of issues has to do with whether you know the surplus. Okay, so in the model I presented, I assume that you know exactly the surplus is equal to 1, normalized to 1. But of course, in most settings, you will have people who are high value and low value. So if you set a high price, you will get the high value guys, but you will lose the low value guys. So in other words, you have a smooth demand function. Okay. And so this is what this particular, this extension. So this is the smooth demand model. Now the value V, the surplus V, is drawn some distribution F, and then if you set a high price, you get the guys. If you set a price P, and you're the only intermediary, you get all those guys with the value larger than V. Okay, that's the trade that happens. So you get a smooth demand function. And this part of the paper that I have actually looks at the smooth demand problem, and it generates a number of nice. So we can do the experiments, etc. Now you have long lines, and you can look at how you price in the smooth demand setting. So that's another direction in which work sort of is moving, and essentially you get very nice you get very nice behavior. Okay, so this is as you expand the distance between the source and destination. This is the distance, and here you get frequency of efficient outcome, that is frequency of trade, and you see that it falls off. Now this, remember, in the benchmark model, you had efficiency always, right? You had 100% trade. But now, as you raise the price, you lower the fraction of people who want to trade. So and it falls off very smoothly and very nicely, and you can compare this to, this is in the lab, and you can compare this to the equilibrium prediction, and you can try and understand.
So you also have a theoretical analysis of this?
Yeah, so we have a complete characterization here.
Characterization.
Yeah, a complete characterization result for this small demand case. And there's some nice properties of this. But that's another line of work where you have a smooth demand. And a third route, a third extension is the following. So now let's go back to the basic model here. So what happens, of course, when you are looking at supply chain, so you're looking at transport problems, is that people care not just about price, but they also care about other features, right? So it may be that people like to take the underground, some people like to take the bus, and so every path has its own demand, and when your path is cheaper, some demand moves, but not all the demand. So in other words, it's a differentiated good. These paths are not perfect substitutes, but they are differentiated. And so now what you can do is you can write down the demand for the path, a particular path, let's say the path U, E, N. The demand would depend on the price of U, E, and N, but it will also depend on the price of the other paths. But it will be a smooth sort of demand system, like a linear demand system, right? So every path is a differentiated good, and every path, there are many people sitting on it, and they are therefore, playing a kind of, pricing game. And when you do that, you write down that problem, you essentially get a linear system, and you can then ask, so essentially the system becomes much smoother, and you can then, ask a number of questions about market power and about how the network structure shapes market power, but you can use all this. There's a very nice and elegant industrial organization model of differentiated oligopoly, and where each good is differentiated from the other. So it's a Bertrand model, but it's not the 0-1 sort of thing, that all I care about is the price. I also care about the good. So it becomes a much smoother model, and you can look at, you can actually study this kind of pricing network problem with that smoother demand setting. And so that's another line of work where you get, a lot of tractability, and you can get unique equilibria, and so you can sort of get nice, it's very elegant to work with that.
You drink equilibrium?
you can get unique equilibrium in.
Because in the other cases, in neither of the two other extensions that you mentioned, you do have unique.
You don't have unique.
But
No.
here when you move,
What happens here is, I don't think I have a. So
that's interesting.
So what happens in this model is that, you can write down the demand. You see, if you take a step back, you will see that the profit will be the price times some demand, and the demand is essentially a linear function of prices of the different parts. So you get a linear quadratic system. Okay, so when you solve it, you get you get a system of linear equations, and under some conditions, you get a unique outcome. Okay, and then you can look at the pricing here as a function of some network centrality measure.
Yeah.
Okay. That's sort of the nature of the exercise. And then you can sort of look at market power in terms of network characteristics.
Mm-hmm.
So let me just. I think I'm kind of, I'm at 11 o'clock, but so. So there are, the other part of this work that I haven't talked about, which I think Fernando was asking, is that you can, instead of having simultaneous pricing, you could have sequential pricing. Okay, so I'm only trading when I own the good. Okay, every time I own a good, I can post a price or I can bargain with you, and so on. So there is a lot of interest in sequential trading in networks, and it uses auction models, it uses bargaining models, and so that there's that sort of work which is also going on, and it's really looking at price formation protocols, which are very different in dynamic pricing rather than what I've been talking about, which is mostly static, one-shot simultaneous pricing. But I just wanted to step back a bit and say that this is really work at the intersection of, if you like, of networks and markets. Okay, and there's a lot of interest at the moment. There's a lot of people doing theoretical work. Some of the work I presented is experimental work, but in fact, there's also a lot of interest in empirical work. There is a group of people who are working in international trade and supply chains, which is mostly driven by empirical concerns, which is a very, very different body of work, but very large and very ambitious. And so this is essentially a very, very active field of work, both at the theory end, experimental and empirical end. Okay. And so if you want to, if you're looking for a topic to work on, I think this is a very good candidate to. So I'm going to stop, but I'm happy to take a few questions.
Sure. I have a quick question about the last point in your conclusion.
Mm-hmm.
You mentioned long distance trade. Do you mean long hop distance, or do you have in mind you're modeling like distance in the sense of trading around the globe, that sense of distance?
Yeah, so
in the context of these applications at the end.
yeah, so one of the applications we have has a following sort of flavor. So what happens in this model is that you have some network and you set a price, and that's the price people have to pay if they go through your node, if they use your service. But the people who go through you could be coming from anywhere. Okay, there's some distribution of demand, and that's just the pairs of source and destination who are scattered throughout the network. Okay, and so what happens in that setting is that it's actually not. It turns out to be not that straightforward to solve for general networks. So what we did was we actually. I don't think we have slides on that, but let me just show you some of the results. So imagine that you are in this ring, okay, and what's happening is that you are this trader, Mr. I. You set a price. The issue is that this price is going to apply to guys who are H and J. It could be H and J want to trade through you. Or it could be G and J want to trade through you, it could be E and J want to trade through you. Okay? So you're setting a price for all of them. And for this specific network, you can actually show that you can only have, so because of the nature of the graph, the zero price is always an equilibrium. Because if everyone sets a price zero, there's nothing I can do. You know, if I set a positive price, people will use the other path, which is the zero price. Right? So that's the simple case, right? But you see that there is also the price one equilibrium. Supposing this guy sets a price one, and everybody sets a price one, okay? Then when H and J have to trade, they will use this guy because it's feasible, and that's the only path that's feasible. So you have the zero equilibrium and the one equilibrium. That's uninteresting, but it's there. The question is, what else can happen? Right? And what you want is, really, is as the ring expands, you want the price to fall, right? If you're looking at the symmetric equilibrium. Why? Because there will be these long paths, and you want trade to occur, but if trade is to occur, these guys have to set a low price. What turns out to be the case, that you can show, is that I think the theorem or the result is that the minimal price is 1/3. The minimal positive price is 1/3. In other words, you can only have 3 intermediaries because they add up to 1, the total cost. As soon as you have, distance going beyond 3, well, these guys are all going to set a price, around 1/3, and then trade breaks down. So that's the sense in which long distance trade breaks down. Okay. So kind of very rough answer to your question.
So you see that therefore in equilibrium there is a lower bound irrespectively of length on the price.
That's right.
Excuse me, and is this one period or multi-period result?
This is one period. This is all static.
Yeah.
Yeah, so the reason is, maybe it has to do with the specific structure we have, but the reason is that when you lower the price slightly, you don't want to lower slightly, you want to lower all the way to get 4 guys to come through, so you want to go all the way to 1/4. There's no point lowering to something between 1/4 and 1/3, because that's not going to get an extra set of trades to be possible. And when you compare 1/4 and 1/3, you can see that it doesn't work out, just sort of computationally. It's better to get 1/3 and have fewer trades than to have a price 1/4 and have that extra set of trades. That's just the margin. Okay.
I have another question. In the case where there is multiplicity, your experience suggests that this really multiplicity, the agents somehow are able to cut their way through and select equilibrium that is essentially a unique equilibrium. So this begs the question of what sort of learning procedures are operating there that make this selection. And I don't want to go to our old mutation type of
Right.
necessarily, but I mean, but the experiment is the experimental evidence is so strong that really that be a natural thing to try to study theoretically.
Yeah, so I think Fernando is asking questions really about this kind of, that split on the efficiency result. So one could ask theoretically, is there a smoother model where the limiting case is this, and in that smoother model you actually pick this equilibrium. Another way to think about it would be the dynamics somehow, is the learning going to pick one equilibrium. And so we haven't done the learning bit, but this smoother linear model actually, what it does is this differentiated paths model.
Mm-hmm.
What it does is it actually, when you take limits, it actually generates these kinds of properties. It actually generates exactly this sort of
Generates limits in the
the
differentiation.
critical guys.
differentiation,
Yeah, so supposing these paths were not perfect substitutes, but they were imperfect substitutes. Okay, these two paths, the long path and the short path and the long path. Then you will get in the unique equilibrium, unique interior equilibrium, an outcome like this, where the critical guy set a high price, the short path sets a high price, and the long path sets a low price.
Interesting.
And when you take these paths to be, there's a parameter which measures the substitutability of these paths. And when you make this parameter take limits, you make them basically substitutable, then the equilibrium would be the critical guys take the whole surface and the non-critical guys get washed out. Which is sort of what you get, so you can select equilibrium, in terms of the theory. So that gets us to that sort of those kinds of results. Yeah. It also gives you some idea about these short path, long path kind of things. So the linear model actually gets us a pretty good handle on these results.
Okay, so I'm going a little bit beyond that. It was worthwhile, and thank you very much.
Thank you.